This denominator is a headache to work with on this integral, but what if I told you that we can actually make a U substitution work in a way that maybe you haven't tried before? Now, before I show you how, I'm David, and I used to tutor students like you back in college before I became a software engineer who's made a really fun Number Ninjas game you can check out below in the description. But getting back to the problem, maybe you tried this particular substitution and got stuck. Now, what do we tend to do? We choose a U value and then take the derivative of both sides. But hold on, because for this problem, that's why you got stuck. Sometimes you got to take your U and do some manipulation first before taking the derivative. Now, I want you to have this mindset. Think about how in this original integral, how do you get dx on the top? Well, you took the derivative of a constant times x to get there, right? So imagine if on this expression on the right-hand side, x was either by itself or just had a constant in front. Now, how do we get there? Well, simple. We work on isolating the variable, and that's what I'm going to go ahead and do here. Let's start off by squaring both sides to get u squared equals 1 plus e to the x. And then I'm going to subtract 1 on both sides, giving me this expression. And what do you know about natural logs? If you want to get rid of e to the x, simply take the natural log of both sides, giving me this. Now, what's awesome is that because the right-hand side simplifies to x, you can now finally take your derivative to find out what our U substitution is going to be. So why this works? Well, on the right-hand side now, we have dx by itself, just like in the original problem on the top, which means now that the dx from the original integral becomes all of this, giving us this new problem to work with. Now, hang on. I know this looks messy because we have two different fractions going on, but the good news is that this simplifies because 2u and u are going to cross-cancel to give us this simpler integral to work with. And maybe you're going to stop here because you already have memorized the formula for this integral. I don't teach memorization on my channel, so if you actually want to understand what to do here, stick around. I'm going to use partial fractions because the first thing I want to do is I want to think about, okay, after bringing this 2 out, let's first factor the bottom because we know it's a difference of 2 squares, u squared and 1. That way now when we have factors in the denominator, for the partial fractions method, our goal is to say, hey, for the original fraction on the left, think of it as the sum of 2 other fractions here on the right, and we just want to find out what a and b are. Now, when you multiply both sides by u minus 1 times u plus 1, that makes it simpler, giving us this. And it looks like we don't have enough information here, but we actually do, because all you have to do is simply choose a u value that knocks out one of these two terms. I'm going to let u equal -1, which gets rid of your a term. And so we'll be left with 1 equals -2b, and it's very simple to see that b is -1/2. And you can try this for yourself too, but if you now choose u equals 1 to knock out the b term, it's very similar because now we get a equals 1/2 this time. And so the integral that had our u terms in them can now be rewritten as a sum of 2 separate integrals, making sure you don't forget this 2 constant that we had factored out. And again, we can simplify things because the numerators and the 2's will multiply through, giving us a difference of these 2 really nice looking integrals, which I hope by now, by inspection, you can see that these are just natural log integrals, right? You get this expression here, and make sure that you put back in what x is. We know u equals a square root of 1 plus e to the x. And also don't forget your absolute value signs and this plus c at the very end. And so I hope this is helpful. If you want more practice before your test, don't miss out on this integral problem.